Alright, so in this video I'm going to talk a little about ethers and their some of their properties and then their nomenclature. So our general ether starts off as an oxygen with our lone pairs bonded to two different R groups. And R groups in this case cannot be a hydrogen. So, what are some properties then that we can say of this ether? Well, if we're to get into salts, such as, let's say, sodium iodide, NaI, when this breaks apart, we're going to have a positively charged ion, cation of sodium, and a negatively charged anion of iodine. Now, since these lone pairs on the ether, we have sort of a dipole moment towards them with slight negative charge. Opposites attract, so obviously the ether is not going to want to solvate this iodine. It's going to want to solvate this cation far better than it will this iodine. Now this can be used for compounds such as KCN. If we look at KCN, you don't want to put something like this in water, because once it dissolves in water, the cyanide is going to pick off a proton, or has a high probability of picking off a proton and creating hydrogen cyanide gas. So what ethers are really good at, especially crown ethers, we can say, we have our crown ether. Because crown ether, as you can see, basic structure, oxygens, and so once we do this isn't the greatest picture, but this is a example of 18 crown 6 ether. 18 crown 6. And potassium just happens to fit, or the potassium ion fits very, very well within that 18 crown 6 ether. So this is a way to increase the nucleophilicity of cyanide in a solvent that's not water, because obviously we put water in there, you've got hydrogen cyanide gas that's more than likely going to be produced. So another example we see this in is Grignard reagents. So we'll just draw our basic structure of a Grignard reagent, where we've got our magnesium, which is a Lewis acid, bromine. Now because this has a slight positive charge on it, remember this is going to act as like it has two lone pairs of electrons coming into attack when they didn't break apart. You're going to have your ethers that are going to solvate this very nicely. And the ether of choice for most of the Grignard reagents is tetrahydrofuran, and it'll come in a solution. You'll have like a 1 molar solution of your Grignard if you were to buy it from a stock place. Now the next part I want to talk a little bit about is nomenclature, because nomenclature is very, very important in chem, especially OChem 2, because that's when you get into much more difficult nomenclature topics. So when we do nomenclature for ethers, we have to remember that ethers have a very low priority. So they're not very important in the grand scheme of things. Not like a cyano group or carboxylic acid; those are much, much higher, along with aldehydes and alcohols. So IUPAC is the one I generally go with, and most of your professors are going to probably be asking you IUPAC names, because they're all trying to change this method because it's much more systematic and not as memorization. There's not as much memorization involved. It's much, much easier. And so with ethers, we have our long chain or more substituted chain being the root name, and our shorter chain or less complex side chain, because we've only got two here, is going to be our alkoxy substitute. And so let's take something like anisole, which is the common name. So if your professor asks you, for example, give me the IUPAC name for anisole. And anisole is this compound right here. We've got a benzene ring, and then we got a methyl. So right now we can basically tell which side has either the longer chain or is much more substituted complex, and it's this side. So our long chain we'd say is a benzene, and our short chain is our methyl. So because it's a methyl group, we like to add methoxy. So remember alkoxy? Just add our alkyl group, which is meth, and oxy. So methoxy, pretty straightforward. So you can name it 1-methoxybenzene, and that is pretty much the general rule for naming some of these. Another one that we can name here, and I'll move up the paper here just a bit for you. Yeah. Okay. Let's say we have this compound over here, where we've got our benzene ring, or a benzene ring I should say. And then let's say, for example, we have it attached to an oxygen and a methyl group. And then we have a double bond here. And then we have another carbon, let's say. And then let's add another carbon. Yeah, and then let's just put an OH here and an OMe here. Okay, so naming something like this. So we want to find the longest chain. And so if we look at this, we know it's attached to a methyl group, we know this ether is attached to a methyl group, and this is the much more substituted chain. So when we look at that, we say, okay, well, we have an alcohol in here, benzene here, so which one gets priority? Well, actually, it's the alcohol that gets priority. And so we'll name this 1, 2, 3, and 4 will be right here. So if we name it this way, which is the correct way, we know we have at positions 1 and 4, we have a di, meaning 2, methoxy substituents. So remember that. So that's our first thing we know. Second thing we know is at the 4 position we have this benzene ring, which, since it's a substituent, is a phenyl. Y and the N mixed up. And then we know we have an OH group here, and our carbon chain is 4, and we've got an ene. So if we're to look at the root, since we have 4 carbons, that's going to be bute. It's going to start with bute, but since we've got a double bond here, it's going to be bute 3 ene 1 all. So this is our base. And then we just simply look at which one for alphabetical order comes before. So our substituents are here. For P, or D comes before P. And so we know that this is simply 1 for dimethoxy. 4 phenyl, bute, so 3 ene 1 all. And that's our basic nomenclature for this compound. So it looks as kind of a big compound, like, oh my gosh, how are we going to name this? Well, it's simple. We just look at the more substituted group for the methyls. We look for priority because of our alcohol here. This is going to have higher priority than this ether. And we just say 1, 2, 3, 4, and then we got a double bond here. So we know that this is our parent chain, and then these are a substituent. And obviously the alcohol is higher priority than this. Otherwise we'd have a whole different name. Alright, now we're going to continue on a bit with a few more examples of ether nomenclature. And with this first compound we'll start with, we want to, since they're all substituents on a ring, we look to determine which one has the highest priority. Well, we know halogens are pretty low on the list, ethers are pretty low, and alcohols are definitely higher than both of them. So just knowing that, we know that this is #1 priority. So we can start here, and this is kind of our 1. If we make this our first and highest priority, which it is, this whole entire ring has the base name of the phenyl. So I like to call that root. Or phenol, sorry, phenol. And then we start looking, we start counting. 1, 2, 1, 2. Well, here we just have a hydrogen, here we have an ether. So we go around the circle like this. And that's at position 3 if we count 1, 2, 3. There's no shame in numbering these on your test or anything else like that. So we know substituents. We have a 3-ethoxy because we have an ethyl group attached. That's what this ETH means. And we have and so we just know that we have the alkoxy substitutes. So ethane or ethyl, so ethoxy. Our other substituent is on our 4th carbon, which is chloral. So 4-chloral. So knowing this, we say, okay, which one has, which one comes alphabetically first? Well, C comes before E, so bring one down. 4-chloral, 3-ethoxy, we don't need a space here, phenyl. We don't need to mark the phenyl as being like phen1-ol because they know that we're just starting from a phenyl and that's #1. The next one we're going to go off of is, this one has stereochemistry. And I know this is drawn a little bit poorly, but this is a methyl going off with a dash. So not out of plane, it's going into the plane. This is coming out of the plane. So right away we can tell that this is our larger, bulkier group. This is our kind of our short chain, less substituted, less bulky. So short chain we can start with is 1, 2, 3 carbons. So that's our kind of our prop. So we know we have a prop, I believe it should be. Yep, propoxy. Yeah. So we have our propoxy. And then our long chain is a bit more complex than sometimes what we normally see. So for that, we know we have a methyl coming off of the pentane. And so since we have a cyclopentane here, and we have a methyl, so we have got 1 methyl cyclopentane. Alright. Now what we need to do is we just need to number these. And so what we do is we can just say that with this methyl group here, this is our first priority. And if we name this as 1, this is 2, this is 3, of a propoxy group, the name is simply 1-methyl because the cyclopentane is our root, is our base, and because of naming as far as M comes before P. 3-propoxy, sorry, I forgot to add a space there, oxy, cyclopentane. Now, there's one last thing we have to do, which is stereochemistry. Now, there's a few tips and tricks that are out there for stereochemistry. One I like is the right-handed, left-handed. And so with this, if you say that my hydrogen is coming out of the plane towards me, so it's jutting up, I can have my thumb be that hydrogen right here. And then I can have my methyl right here being my first priority group, all right? And then I know that my next highest priority comes on this side, not this side. So when I move it like that, my hand closes in. And this is my right hand. This is then an R configuration is how you learn it. However, if your group was over here, let's say, your propoxy group was over here, your left hand would be better because your hydrogen's up with your thumb, going your fingers going down to meet the methyl group, and then curving around, and that would be S. Same way with this third carbon, the propoxy. If you imagine that your finger is down and you're moving it up, you're still closing it this way because your priority group isn't over here, it's over here. So bring your thumb down here, because the hydrogen's going into the plane, or yeah, into the plane, not out of. And then your next highest priority group is over here, so you just close it like this, and voila, still your right hand. So what we'd say for these is 1R, 3R. And this is a pretty neat way to do this. I know on a lot of my exams, you'll look up and you'll see students going like, this, and it's kind of funny, but it works really, really well. Now let's do a little bit of epoxide nomenclature, because this is much more difficult in my experience, simply because the book I was reading wasn't all that good. So if we take an epoxide ring like this, and epoxides can be formed from alkenes, MCPBA, treating it with that. Count your carbons. How many carbons do you have here? Oh, we have carbon 1, carbon 2. Oh, pretty easy. That means my root name is going to have at least ethane, something like that, right? Ethane. But it's an epoxide. So what you do is you say, oh, well, it looks like it's 1, 2, 1, 2 epoxy ethane. 1, 2 epoxy ethane. So another type of epoxide nomenclature that I want to take you through is, let's say we have an epoxide that looks something like this here. These are ethyl groups, and this can be a little isopropyl group here, and then we just have a little hydrogen hanging off that end. So if you were asked to name something like this, we're going to start with our long chains. So let's just start over here. 1, 2, 3, 4, 5, 6. So we count our carbons. 1, 2, 3, 4 again, 5, 6. Double counting just to make sure. You don't want to lose points on a test because you forgot that. So our root name is hexane. Substituents, if we circle, I encourage you to always circle the parent chains. Our substituents are 2-methyl, and we also have a 4-ethyl. We know that our epoxy substituent is at the 3-4 position, because 3, 4. So 3, 4 epoxy. Alright, so now that we have that in order, we can just kind of name it. Well, epoxy comes before ethyl, so if we want to name this, we just say, oh, 3, 4 epoxy, 4 ethyl, dash in there, 4-ethyl, 2-methyl, hexane. They start off kind of daunting, but they're not actually too bad. The epoxide nomenclature isn't too difficult.